Hey, my name's Josh and I'm going to be presenting the experiment ME1, which is mechanical to electrical energy, and I'm going to be demonstrating part A of it. Before we get onto the actual experiment, I will explain to you what everything is and all of the bits and pieces that we're going to need. So you can see here I've got a string in my hand. It might be a little bit difficult to see on the camera, but in each end I've tied a knot. So just a fairly large knot on this end, and then I've tied a knot which also has a loop on the end here. The first thing I'm going to need to do is measure the length of this string from one knot to the other knot. And I've already gone and done that. That's 50 centimeters for this particular string. Now I have a bunch of masses over here. They range from 10 grams through 200 grams. And I also have a generator up here. So the generator has two pulleys on the end. One of them's large, one of them's small. And the experiment is going to be picking any mass from here, and I will put the mass through the loop here and wind it up around the pulley and just let it drop. Now, a couple things before we go on and actually do the experiment. I believe that in the instructions for this experiment, it tells you to use the large pulley. I am going to be using the small pulley because it will give me more accurate results. This experiment is notorious for giving really, really bad results, and the reason for that is because we need to record the time that it takes for the string with the mass attached to pull all the way through the pulley. If that result is recorded even slightly wrong, we start getting accelerations of that mass that are greater than the value of g. And when that propagates through, and when it comes to calculating the efficiency of this generator, it ends up being at over 100% efficient, which would be really nice given that it means we're creating energy, but it's not particularly feasible. So what I'm going to do now is I'm actually going to do the experiment. And we need to wind this up. Okay. Once we've wound it up, we make sure that the bottom knot is level with the center of the pulley. And I'm going to come over here to Pasco, and I'm going to push record, and then I'm going to drop the mass. So I push record, and I drop the mass. And then stop recording. You can see we get this graph here, which has a bunch of separate peaks. The very first thing that I need to do is I need to record the time that it takes for the pulley to pull, for the string to pull all the way through the pulley. So I need to use what's called a coordinate delta tool here. So I click on this, and it's really important that we zoom in right down here, and we pick the point right when the pulley starts to rotate. So that's this point just here. Then we're going to zoom out again, and we're going to pick the highest peak on this graph. The highest peak is when the pulley is spinning the fastest and therefore generating the most energy. That means that the highest peak will be when the string finishes pulling through the pulley. So we get another coordinate tool, and we select this peak here. That means that the time taken for the string to pull through the pulley is 0.91 seconds minus 0.470 seconds. Now, with this prac, we actually provide you with an Excel spreadsheet to calculate everything. So we can just fill in all of the orange columns, and that will calculate everything for us. So the mass is 20 grams, so that is 0.02 kilos. Make sure you record everything in kilograms, meters, and seconds. That's really, really important. And the height was 0.5 meters. The time was 0.921 minus 0.470. And finally, the electrical energy, which is the energy produced, is the area under the graph. and that is this value just here. So that is 0.03598. And hopefully, when we put all of this in, we get a value of the unaccounted for energy. Fortunately for us today, that unaccounted for energy is actually positive. There are many times doing this prac, particularly if you use the large pulley wheel, that this value is actually negative, and that would imply that we are generating energy. In this case, it's not, which is good. We can also see that the acceleration is significantly less than the value of gravity's acceleration, so that is also really good, meaning that our results should be fairly accurate. One thing to note is that the uncertainty of the kinetic energy falls outside of what the maximum uncertainty should be theoretically. So that's not ideal, but it is what it is. Unfortunately, experiments always come with an inherent amount of error in them, and we just have to deal with that. Now, then it gives us the efficiency all the way at the end. So that allows us, that means that our generator is 37% efficient for a 20 gram mass. Now, you can see here there are a lot of different bits of data to record. So if you were here, you would have to do this for at least 5 different masses with the same length of string, and then you would have to do all of those masses again with a different string. So you would do 5 masses with 3 different lengths of string, being 15 measurements in total. You will also, in your performer, you will need to graph this graph here. And once you've got all of the data and calculated all of the efficiencies, you will need to graph the efficiency for each length of string against the mass. You will want to do all of this on one graph, and you'll get 3 separate lines, and you should come up with a trend between the relationship between the efficiency and the mass of the weight on the end of the pulley. And that is basically all of this prac. So thank you guys, and best of luck with your prac.